Welcome to the deep dive. Today we're going to try and cut through some of the usual quantum complexity.
Yeah, straight to the point.
Exactly. We're tackling a concept that's actually incredibly elegant, really, the two-state system.
Mm.
Our mission here is simple. We want to show you that whether you're looking at, say, a single electron spinning around,
Or chemical bond holding things together.
or even the forces inside an atomic nucleus, you're often looking at, well, fundamentally the same mathematical problem. It's like a universal quantum toolkit.
That really is the beauty of it.
Yeah.
I mean, look, the real world is, of course, incredibly complex. Molecules wobble, atoms bump into each other in countless ways.
Right, infinite variables.
But for a surprising number of systems, we can get a really, really good handle on their behavior by simplifying, by approximating them as having only two main internal states that matter.
So you focus just on the two most important states.
Pretty much. Often these are systems with two energy levels that are really close together. And if we can just figure out the math for those two states, suddenly the physics of the whole system becomes much, much clearer.
Okay. Let's walk through the mechanics then, but keep it conversational. So any quantum system has a total state, right? And in this simplified picture, that state is just like a blend, a mix of two basic options.
Exactly. Let's call them state 1 and state 2. The system's overall state, which we write as vols in base arl, is just some amount of state 1 plus some amount of state 2.
And those amounts are the amplitudes, CNN and CO2.
That's right. Complex numbers technically, but they tell you how much of each base state is in the mix at any given time.
And how that mix changes, how it evolves over time.
Yep.
That's where the Hamiltonian comes in?
Precisely. The Hamiltonian H governs the dynamics. Think of it like a set of rules in matrix form. You don't need to visualize the matrix itself, but it has different parts. You've got the diagonal parts, H infinite and H $22. These basically tell you the energy the system would have if it were just in state 1 or just in state 2 all by itself. Kind of the baseline energy.
Makes sense. And the other parts?
The off-diagonal parts, H $12 and H $21. These are, as you said before, where the action really is.
Because they link the two states?
Exactly. H $12 represents the amplitude, the possibility for the system to transition, or you could say jump from state 2 into state 1, and H $21 is the jump from 1 to 2.
The jumping probability you mentioned.
Well, technically the amplitude for the jump, but yeah, that's the idea. And the whole game, really, is finding the true energy states of the system when this jumping is allowed. These are the stationary states, AV solars and EII. They don't change in time.
And finding those two energies, EDI and EI, and what combination of state 1 and state 2 corresponds to them. That's the core challenge.
That's the core challenge. Everything we're going to talk about, from chemistry to electron spin, boils down to how that possibility of jumping, that off-diagonal term, affects these final energy levels.
Okay, let's make this concrete. Chemistry feels like a good place to start. You said it's maybe the clearest example of this exchange idea in action. The hydrogen molecular ion, tech stage 2 plus Staller.
Perfect example. It couldn't be simpler, really. One electron shared between two protons. That's it.
So visually, I'm picturing two protons, let's call them A and B.
Good. So base state 1 is basically the electron hanging out near proton A.
And state 2 is the electron over near proton B.
Exactly. Now, if those protons were, miles apart, the electron would just sit near one or the other,
Yeah.
and the energy being in state 1 or state 2 would be identical. No difference.
But we're talking about a molecule, so they're close enough to bond.
Right. And when they're close enough, that electron isn't stuck. It can actually tunnel through the potential barrier between the protons. It can jump back and forth.
Wait, hang on. Are you saying the entire reason there's an attractive force, that the chemical bond itself is just because the electron can tunnel between them? That feels too simple.
It sounds simple, but it's profoundly quantum mechanical. Absolutely.
Yeah.
When the electron can jump, meaning that off-diagonal term, H12 is not 0, it mathematically links state 1 and state 2.
Okay.
And that linkage forces the energy levels to split. Instead of one energy level for either state, the system now has two distinct possibilities: a lower energy state, EII, and a higher energy state, EI.
Ah, the energy splitting. And the lower one, EIHO, that's the stable one. That's the bond.
The bonding state, yes.
Yeah.
The system finds a lower, more stable energy configuration precisely because the electron is shared and exchanged between the two protons. It literally pulls the protons together to achieve this lower energy. We call it the quantum mechanical exchange force.
So if the electron somehow couldn't tunnel, if H12 was 0.
No bond. Simple as that. The higher energy state, EII, actually corresponds to a repulsive force pushing the protons apart.
Wow, and the strength of the bond just depends on how easy it is for the electron to jump.
Essentially, yes. The stability depends on the magnitude of that exchange term, often called dollar. A larger dollar means a bigger energy gap between EI and AEI, and usually a stronger tendency to bond.
Okay, that H2 plus example really clicks. Now, you mentioned this isn't just for molecules. We can scale this idea up even to nuclear forces.
We can use the same mathematical framework, yes. Think about the strong nuclear force holding protons and neutrons together in a nucleus. It can be viewed analogously as another kind of exchange process.
But what's being exchanged there? Not an electron, surely.
No, not an electron. The idea, pioneered by Yukawa, is that the force is mediated by the virtual exchange of a different particle, a pi meson or a pion.
A virtual exchange. What does that look like? Can you describe that?
It's a fleeting process. Imagine a proton. It can momentarily transform into a neutron plus a positively charged pion.
Okay.
Less than, this pion then quickly jumps across the tiny gap to a nearby neutron. The neutron absorbs the pi plus dollar, and in doing so, it turns back into a proton.
So the net effect is that the positive charge hopped from the first particle to the second.
Exactly. A proton became a neutron, and a neutron became a proton by exchanging this pion. It's like an electrical charge exchange.
And mathematically, this pion exchange plays the same role as the electron jumping in H2 plus red. It's the off-diagonal term in the nuclear Hamiltonian.
That's the analogy. It links the states, like proton-neutron versus neutron-proton, and leads to an energy splitting, resulting in the attractive strong force. Same two-state math, vastly different scale and particles. Amazing, isn't it?
It really is. Okay, let's step back to chemistry, but add a layer of complexity. From text2 plus dollar to the neutral hydrogen molecule, text2, now we have 2 electrons and 2 protons.
Right, and adding that second electron brings in something absolutely crucial, the Pauli exclusion principle.
Because electrons are identical particles, fermions.
Identical fermions, yes. And that means there are strict rules about symmetry. When we define our 2 base states now, which basically involve just swapping which electron is associated with which proton, the overall quantum state, the wave function, must change sign. It must be antisymmetric if you swap the 2 electrons.
Okay, antisymmetry required. So how does that constraint, the Pauli principle, actually influence the chemical bond? Does it, decide if the bond forms based on spin?
It does, fundamentally. It connects the electron spins to their spatial arrangement and thus to the energy. Let's break it down.
Please.
Case 1. The 2 electrons have opposite spins. One spin up, one spin down. We call this the singlet state, total spin 0.
Okay, spins paired up.
For the total state to be antisymmetric overall, as required by Pauli, the spatial part of their wave function must actually be symmetric under exchange.
Symmetric spatial part.
And it turns out that this symmetric spatial arrangement corresponds mathematically to the lowest possible energy solution, EI. That's the stable covalent bonding state of the text H22 molecule.
So the Pauli principle essentially forces them into the bonding configuration because their spins are opposite.
That's a great way to put it. The spin state dictates the required spatial symmetry, and that symmetry leads to bonding.
Wild. So what happens if they try to come in with the same spin, both spin up, say, the triplet state?
Right, parallel spins, total spin 1. Now, for the overall state to still be antisymmetric when you swap the electrons, the spatial part of the wave function must itself be antisymmetric.
Antisymmetric spatial part this time.
And mathematically, that antisymmetric spatial state corresponds to the higher energy solution, EII. This state is repulsive. It pushes the protons apart. No stable bond forms.
So the 2-state analysis, combined with Pauli, shows that the hydrogen molecule is only stable if the electron spins are paired. The spin pairing enables the bond.
It's a direct consequence of the symmetry rules for identical particles. Amazing interplay.
Okay, this framework is clearly powerful for simple molecules. Does it extend further? You mentioned resonance in bigger molecules, like benzene.
Absolutely. Benzene, that classic 6-carbon ring, is famous for being unusually stable. The 2-state model gives us a beautiful explanation why.
How does that work? What are the 2 states for benzene?
We often draw benzene with alternating single and double bonds, right? But there are 2 ways you can draw that pattern around the ring. They look equivalent.
The Kekulé structures.
Exactly. Think of those 2 equivalent drawings, those 2 Kekulé structures, as our base state 1 and state 2.
But benzene isn't actually flipping between those 2 drawings, is it?
No, the real molecule, its actual ground state, isn't one or the other. It's a mixture, a quantum superposition, a linear combination of both base states.
Ah, so that's resonance. The true state is the lowest energy stationary state, EI dollars, which is a blend of the two possibilities.
Precisely. And because the system can effectively access both configurations, meaning the electrons are delocalized, and the off-diagonal term H12 linking the two Kekulé states is significant, the resulting energy EI is considerably lower than the energy of either single Kekulé structure would be on its own.
And that extra lowering of energy is the resonance stabilization energy that makes benzene so unreactive.
That's it. It's a direct outcome of the two-state mixing.
Okay, and this mixing doesn't just explain stability. You mentioned it can even explain color in dyes.
Yes. Take a complex organic dye molecule, like, say, dye magenta. Many dyes have structures that allow for a similar kind of two-state description, often involving charge separation or electron distribution.
So again, we have a lowest energy state, ETLers, and a next higher energy state that come from mixing two base states.
Exactly. Now, the energy difference between these two states, EII, is crucial. For many dyes, this energy gap happens to fall right in the range of visible light photons.
Okay, so what happens when light hits the dye?
White light contains all colors, all energies. When that light hits the dye molecule, the molecule can absorb a photon if that photon's energy exactly matches the gap EII. It uses that energy to jump from the ground state EI up to the excited state EI.
So for magenta dye, it absorbs photons with a specific energy.
Right. For magenta dye, that energy gap corresponds to photons in the green-yellow part of the visible spectrum, so it strongly absorbs green and yellow light.
And if it absorbs the green and yellow, what we see is what's left over.
Exactly. The light that gets transmitted through the dye, or reflected off it, is now missing those green-yellow wavelengths. What's left is primarily the red and blue parts of the spectrum.
Yeah.
And red light plus blue light.
Looks magenta to our eyes. Wow. So the color is literally determined by that energy splitting calculated from the two-state model.
It's a direct prediction. The quantum mechanics of the two-state system dictates the color we perceive.
Okay, let's completely shift gears now. Away from chemistry towards something maybe more fundamental. The behavior of a single electron spin in a magnetic field. That's another two-state system, right?
A perfect classic example. The electron has intrinsic angular momentum, spin, which acts like a tiny magnet. In a magnetic field math BFBP, it basically has two primary states, spin pointing generally along the field, low energy, or spin pointing opposite the field, high energy.
We usually call these spin up, Vol.3 plus wrangle, and spin down, Dalvert wrangle, along some chosen axis, like the z-axis.
That's the standard convention, yes. Those are our base states, state 1 and state 2.
Now, if the magnetic field math BFB lows was pointed only along that z-axis,
then the Hamiltonian would be simple. Only the diagonal terms, h-live and fast and h22 dol, would be non-zero. They'd just represent the energy difference, proportional to Pauli, between having the spin aligned, h-live on lower energy, or anti-aligned, h22 higher energy, with the field.
So no transitions. The spin would just stay up if it started up or stay down if it started down.
Correct. Just two fixed energy levels, boring dynamics.
Now, what if the magnetic field isn't perfectly aligned with Z? What if it has components in the X or Y direction too? A transverse field.
Ah, now it gets interesting. The moment you have Bill-Vollard-Bohl components, the off-diagonal terms in the Hamiltonian, H12 and H21, suddenly become non-zero.
And those are the jumping terms.
Exactly. These terms, proportional to $98, provide the amplitude for the spin to flip from up to down or from down back up again. They couple the two states.
So let's say I prepare an electron that's definitely spin up along D's. Then I switch on a magnetic field that's pointing, I don't know, diagonally. What happens?
Because those off-diagonal terms are now active, the system won't stay purely spin up. The amplitudes C-tol and dollar spin-ups for spin-up and C-tol2 for spin-down will start to oscillate back and forth over time.
So the probability of finding it spin up or spin down changes rhythmically.
Precisely. It oscillates between purely up to some mixture, maybe purely down, back to a mixture, back to purely up.
And if we think of the spin as a little vector, what's it doing?
That oscillation corresponds to the spin vector precessing. It rotates, like a tilted spinning top, around the direction of the total magnetic field vector math PFBI.
And the speed of that rotation?
That angular frequency, omega, is determined directly by the energy splitting between the two stationary states, which in turn depends on the strength and direction of math BFB through those Hamiltonian elements.
So the two-state math gives us a complete picture of spin precession, something that sounds really quite esoteric, but it's just two states interacting.
It provides a complete deterministic mechanical description of how the spin behaves over time. Again, starting from just two base states, and the rules linking them.
This is really quite something. The mathematical unity here is striking.
Isn't it?
Yeah.
Well, let's just quickly recap. We've used the exact same fundamental two-state mathematical structure to understand. One, chemical bonding, like in text 2 plus dollars, through this idea of quantum exchange force.
Right.
Two, the role of symmetry and the Pauli principle in making the text A2 molecule stable only when spins are paired.
Got it.
And three, the fundamental dynamics of how an electron's spin precesses rotates in a magnetic field.
So the ultimate takeaway, if I'm getting this right, is that the physics might look totally different. Chemistry, nuclear physics, magnetism, but underneath, if it can be approximated as two dominant states interacting.
Then the underlying math is identical.
Once you understand how that jumping term, that H12 links the states and splits the energies, you've basically solved the core problem for all these different systems.
You have the key. It shows the incredible power of finding the right simplification, the right approximation.
It makes you wonder.
It does. It poses a really interesting question, I think, for you to consider. How many problems out there, things that seem incredibly complicated, whether in science or maybe even elsewhere, could actually be understood much more clearly if we could just identify the right two key states, if we could boil them down, effectively, to a two-state system? It's a powerful, simplifying lens.
Definitely something to think about as you look at the world around you. Well, thank you for joining us on this deep dive into the surprisingly universal power of the quantum two-state system.
With pleasure.
We'll see you next time on The Deep Dive.